Hey there, how are y'all? Today we're going to look at 1.3 on the real number system. The objective is that you'll be able to classify real numbers and determine if a set is closed under certain operations. And so we're going to look at the number system today and just kind of remind ourselves of what the different sets of numbers are and how they interrelate with each other. And so remember first the natural numbers. Natural numbers are also called our counting numbers. They start at the number 1. And they go 1, 2, 3, 4, 5, and go on forever, right? I mean, they don't stop. I mean, you can go to a million and a billion and a trillion and keep going, right? Natural numbers. Now, the next set that we have are called the whole numbers. And these include all natural numbers and 0. So it goes 0, 1, 2, 3, 4, 5, and so on. Again, it starts at 0, but it doesn't have an end. We look at the integers. Integers are whole numbers and their opposites. That's the definition of it. And so what does that mean? Well, the whole numbers, again, were 0, 1, 2, 3, so on. And what are opposites? Well, opposites are numbers that the sign has changed. So if I have positive 1, its opposite is negative 1. And if I have positive 2, its opposite is negative 2. And so when we look at integers, we're looking at numbers like negative 2, negative 1, 0, 1, and 2. And so that list will go on forever in both directions. So we're going to go out all this way, and we're going to go out all this way, and have negative numbers forever, positive numbers forever. There's no start point, there's no end point, because we can always have a higher positive number and then have its opposite on the other side. The next couple sets of numbers, these next two, very important, rational numbers. And so I want you to look at the root word ratio that's in there. And remember that ratio is another word for quotient. And so this is that all real numbers can be written as the quotient of two integer numbers. So you see that this definition here implies this definition here, right? And so all real numbers can be written as the quotient of two integer numbers written as a fraction. That's what quotient means, right? Because quotient is division, as long as b is not equal to 0. So I could take like negative 5/3, that is a rational number. I could take 7/9, rational number. 10 billion over 5, rational number. Because again, it is the quotient or the ratio of two integer values, as long as the denominator is not equal to 0. Now, I'm going to skip for a second irrational number and go to real number. So a real number is any number that has a location on the number line. So if I could plot that point on the number line, be it 0.1 or the square root of 2, and the square root of 2 can be put on the number line because it's 1.41, so on, right? I can put that on the number line. Real numbers, anything you can put on the number line. So let's backtrack. So rational numbers were numbers that I could write as a fraction, right? So something I could divide and get. So like 4 over 2 reduces to 2, so it's on the number line, right? 7/3 is 2 1/3. I could put it on the number line. I could write it as a fraction, so we get that one. But what about like a number like square root of 2, which if you go to your calculator and you get it, the decimal looks like it doesn't repeat. Well, that's because it doesn't. And the decimal won't stop. And so irrational numbers are all the other real numbers that cannot be written as the quotient of two integer numbers. And so numbers like pi or the exponential base, so that'll be represented by the letter E, and we'll talk about that later on. All of those type numbers will be irrational. So as we move along here, we're going to look at two separate diagrams. We're going to fill this out together. And so the first one on the left is kind of an organizational chart of how the numbers interrelate. We're actually going to do this one in class together because trying to do it over this video is going to be a little hard, and I want you to understand the intricacies of how the numbers interrelate in the number system, in the real number system. This diagram in the green on the right is one that you've probably seen before. And so this box we're going to fill out here. And so understand that every real number could fit in this box. Just imagine for yourself that every real number could fit in this box. And then remember that we said that all real numbers separate into one of two categories. One being rational numbers, the other being irrational numbers. And so rational numbers are going to be over on this right side with the bubbles that are inside. So all rational numbers over here. And then over here, we have all irrational numbers. And so, again, that's our split of real numbers. Every real number, that's everything in the big box, right, will be able to separate either into a rational number or an irrational number. Now, under rational numbers, think about our definitions for a second. We said that all rational numbers could be written as the quotient or the ratio of integer values, right? And so all integers are going to be contained within the rational numbers because we have to have those integers in there. But then integers were defined as what? All whole numbers and their opposites. And so all of the whole numbers are contained inside the integers. So again, here I would have numbers like -2 or +7, right? But this +7 would also end up in this whole number range, right? And then this last bubble down here is the natural numbers. And so this 7 is a whole number, but it actually falls all the way through. Grabbing the wrong one there. So whole number's going to stay there. I'm going to grab this box. Whole numbers actually, the 7 actually falls all the way into natural, right? The only whole number that's not natural is 0. We've got integers that are not 0 or positive would be negatives inside this part of the bubble. And out here in rational numbers, yes, -2 and 0 and 7 are rational numbers, but we also have numbers like 1/2, right? Or we have numbers like 3.4, right? Both of those are rational numbers, but they're not integers, they're not whole numbers, they're not natural, right? Over here under irrational numbers, we're going to have numbers like the square root of 2, right? Because the square root of 2 is not rational for sure, but we can put that on the number line. Another number that we'll have here is pi, right? So we can have either of those in our number system. So there's pi. All right. So again, we're going to look at this other flowchart in class. I want to do this with y'all because again, it's a little different than what you might be used to. So this is the next section I want you to look at, and this is a little practice for y'all. There are 4 questions here. Obviously, you can see the numbering has kind of messed up, but I want you to try each of these questions. So in number 1, the first number 1, it says give a 3-digit number for each of these categories. So again, only 3 digits. Now, you can use a decimal place anywhere you want. You can use other symbols anywhere you want, but you can only have 3 digits. No more, no less. And so, for example, in part A, I want you to write a rational number that is not an integer. And so if you think about that flow chart that we just had, right, that Venn diagram, what numbers would be rational but not an integer? In the second one, and I'm going to see if I can get these numberings to fix themselves. This one should be B. An integer that's not whole. So think about what integer is not a whole number. And then finally, looking for a natural number in this last one for the first number 1. In the second question here, name the only whole number that's not a natural number. So think about what we just said before. Go back in the video if you need to. And then this one, is 0.12 repeating a rational or irrational number? And I want you to just think about what that would be and why is it in this category? And again, if you're struggling with that, we'll talk about it. And then finally, last question, name a number that has a special symbol that is irrational. Again, we've talked about that before in this video today. All right, so try those 4 questions, and then in class, we're going to go and use those numbers. So again, write out some numbers that you think. If it's wrong, that's okay. I want you to try something. I want you to have an idea of what this might be. So now that we've talked about sets of numbers, we need to talk about another term that comes up. And it's one that we don't talk a lot about often, but it is important to what we're doing. And so a set of numbers, the word we're going to use here is closed. So a set of numbers is closed under an operation if the result of the operation on any 2 numbers in that set is also a number in that set. So it's a weird definition a little bit, right? And if you understand the math behind it, it makes sense, but obviously you probably are like, what? So what does that mean? Let's look at this example below. And we want to determine if the set of -1, 0, and 1 is closed under addition. And so again, to be closed, I can only have certain inputs, and all my outputs have to be in the same group of numbers as the inputs. So in this case, to be closed for addition of -1, 0, and 1, I have to be able to add all them together in different orders and never get a value that is not -1, 0, or 1. Because if I get a value that's not those, it's not closed. So let's look at the first pair and see what happens. And actually there's 6 pairs here, right? So if we scroll down, you'll see all 6 pairs. And so pause the video real quick and get these answers. It's not going to take you long. All right, so let's look at these. What is -1 plus -1? Well, -1 plus -1 is what? It's -2, right? And -1 plus 0 is what? -1. And -1 plus 1 is 0. 0 plus 0 is 0. 0 plus 1 is 1. And 1 plus 1 is 2. So for these 4 in the middle here, it works out, right? This one, this one, this one, and this one. Those all work out because the answer comes out to a number in our set that we started with. It's either -1, 0, or 1. The problem comes in, that is not the button. Sorry about that, but the thing we would need to look at is these two. This one comes out to -2 here, right? This one comes out to +2. So is this closed under addition for -1, 0, and 1? No. If I get just one answer that doesn't come out in that set, closure is not available to us, okay? And so that's what we're talking about when we talk about closure. It is if I have a certain set of numbers, does every answer come out in that set of numbers? And so we're going to look at some operations in class. You'll see as we scroll down, we're going to do this table together, so don't worry about filling it out now. We're going to do this table together in class. But that is the notes for this section. If you've got questions, again, ask. And I hope y'all are having a great day.